All right, everybody, welcome back. In this exciting episode, we're going to take a look at how to integrate some funky trigonometric integrals. We're going to kind of look at three different parts in this thing, okay? So the whole section is called trigonometric integrals. We're going to focus on powers of sine and cosine, products of sine and cosine, as well as products of secant and tangent within integrals. So in the first part, we're going to look at powers of sine and cosine. So no better way than to just jump into some examples. So suppose we want to find the integral of sine squared x dx, okay? Well, this ties directly into integration by parts, and that's what we're going to use. Use substitution is not going to help us here. If you was sine, d, you would have a cosine in it. And that just doesn't help us here. So what we're going to do is we're actually going to think of this as sine of x times sine of x dx, okay? We'll break it into two parts, and now we're going to use integration by parts. So I'm going to let u be one of the sine x's. I'll let dv be the other sine x and the dx, okay? Now just be careful. When you take the derivative of sine, you'll get back positive cosine x. When we integrate sine, we'll get back negative cosine of x, okay? So let's see what happens here now. So we have this integral of sine squared x dx becomes, okay, u times v, negative sine x cosine x, minus the integral of v du. So that's going to be negative cosine squared x. Okay, I'm going to take care of that double negative. Well, what happened? We traded a sine squared integral for a cosine squared integral. So what are we going to do to get around this? I'm actually going to use the Pythagorean identity to get that back in terms of sine squared. So let's take a look here. We've got negative sine x cos x plus the integral of 1 minus sine squared x dx. Okay, when I use my Pythagorean identity, I get that back in terms of sine. What I'm now going to do is break this into two separate integrals. So I've got integral sine squared x dx equals negative sine x cos x plus the integral of 1 dx minus the integral of sine squared x dx. This now is something we can integrate. That'll just kick back an x. But the thing to notice is that we now have a form of the original integral on both sides. We're going to add that back to the left side now. And so what do we now have? We have two of these integrals of sine squared x dx is equal to negative sine x cos x. When I integrate the 1, I get back a plus x. I'll throw the plus c in there because those are gone. And now divide by 2, and we get that the original integral of sine squared x, I'll write it like this, negative 1/2 sine x cos x plus 1/2 x plus c. When you multiply c by a half, it doesn't really change. It's still just some arbitrary value. We leave as c. And there you have it, okay? So the idea was to get through this integral, we broke up the sine function. We did a little bit of trig substitution, and then we were able to go through. Okay, let's take a look at the next example, which is just this beefed up a little bit. Let's take a look at the integral of sine cubed. See what happens, and then we'll kind of formalize this into a formula. So what I'm actually going to do here is I'm going to do what I did last time. I'm going to break it up. This time I'm going to break it up into sine squared x times sine x dx. Okay? I'm going to let u be sine squared x. I'm going to let dv be the sine x dx that's left, okay? So now we've got to be careful taking the derivative of this. We got to use the chain rule. We'll get 2 sine x to the first times the derivative of sine, which is cosine. Integrating dv, we get back negative cosine of x again. All right, putting everything together, integration by parts. uv, next time, negative sine squared x cosine of x minus the integral of v du. Well, notice when I multiply these, I'm going to get negative cosine squared x, actually negative 2 cosine squared x sine of x dx back here, okay? And so, again, what I'm going to do, let me rearrange this. First of all, that's going to be a plus because of the double negative. And I'm going to write it like this. I'm going to write it like this, the 2 sine and the cosine squared after it, okay? But now what we're going to do, like we did in the other ones, we're going to replace the cosine squared that showed back up in the original integral with 1 minus sine squared. So let's see what that does for us. Okay, so we're going to have 2 sine x, 1 minus sine squared x dx. I'm basically going to distribute this 2 sine and break it up into 2 separate integrals. So I'm going to have plus twice the integral of sine x dx, that's this one, and then minus twice the integral of sine cubed x dx, right? When I multiply this by sine squared, we get sine cubed x. And that's actually what we want, because now, again, we have this sine cubed integral on both sides. This time I'm going to add the 2 sine cubed. And what do we got here now? We've got 3 of these sine cubed integrals equal to negative sine squared x cos x. And I got to bring this down, plus twice the integral of sine of x dx. Well, we can integrate that. So 3 of these is equal to this. Integrate 2 sine, get back negative 2 cosine x. Divide through by 3 this time. Negative 1/3 sine squared x cos x minus 2/3 cos x plus c. And there you have it. Okay, and this is the idea, and this is known as the reduction formula for sine and cosine. Okay, and so what we can do is kind of boil this down to, it's a process, and this is how it works. Okay, these are called our reduction formula for powers of sine and cosine. Okay, so the way it works in general, if we have sine to the nth power of x, okay, we're going to break that up into sine to the n minus 1 power of x times sine of x dx. This will become the u portion. This will be the du portion, or the dv portion, I should say. When I integrate, I'll get back negative cosine of x. Now, for the du, bring down the power, n minus 1, sine to the n minus 2nd power of x, times the derivative of sine, which is cosine of x dx. Okay? So let's see what happens now. Bear with me. We get sine to the nth power of x equals, okay, so we've got this integral, we've got u times v. I get negative sine to the n minus 1st power of x cosine of x minus the integral of v du, which is this mess. Now look, this is going to be giving us a cosine squared when we multiply. All right, so I'm going to have negative n minus 1 sine to the n minus 2nd power of x cosine squared x dx. Cleaning this up, I'm going to bring that coefficient out front. So we have negative sine to the n minus 1st power of x cos x plus the coefficient n minus 1 integral sine n minus 2 power of x cosine squared x dx. At this point, we replace cos squared with its Pythagorean identity. And now from here, I'm going to distribute the sine to the n minus 2 power through and break this into 2 separate integrals. So we get sine nth power of x dx, negative sine to the n minus 1st power of x cos x, plus n minus 1 integral. Okay, when I distribute to the 1, I just get sine to the n minus 2nd power of x. When I distribute to the next one, sine to the n minus 2 times sine squared is just sine to the nth. So minus the integral sine to the nth power of x dx. We got back an integral in terms of what we started with. Oh, and I got to be careful. There's this coefficient right here that I got to make sure I distribute to both. Okay, I missed it. I'm going to squeeze it in right here. That's n minus 1 power gets distributed to both of these integrals. So there's an n minus 1 power in front of this, okay? And so there's that repeated integral though, okay? And so what are we going to do? We're going to add n minus 1 of these to the other side. What's one of these integrals plus n minus 1 of these integrals? Well, 1 plus n minus 1 is just n, so we end up with n of the integrals of sine to the nth power of x. Bringing all this down, negative sine to the n minus first power of x cos x plus n minus 1 times the integral of sine to the n minus second power of x dx. Now, to get this original integral by itself, I would divide through by n. So the integral of sine to the nth power of x is negative 1 over n sine to the n minus first power of x cos x plus n minus 1 over n integral sine to the n minus second power of x dx. Then, with whatever's here, if we need to, we repeat the process. If we can get down to sine to the first power, we can integrate that. That's negative cosine. If we get down to the sine to the 0 power, that's just the number 1. We can integrate that and get back x. So from here, you kind of go on and repeat the process, okay? But this is your reduction formula for any power of sine. Similarly, for cosine, it works pretty similarly. I won't go through the whole process. I'll just give it to you. It becomes cosine n to the x dx equals. This is positive 1 over n. Cosine to the n minus first power of x sine x stays plus here and becomes cosine to the n minus second power of x dx. These, like I said, are your reduction formula. Okay, so instead of doing like integration by parts a whole bunch of times, now let's see how using this formula works to do something like the integral of cosine to the fifth power of x, okay? So now, like I said, instead of breaking this all up like I did the first two times, we've kind of generalized this into this process, okay? So n is the power. So look, here n is 5, okay? We have power of 5. So look, following the formula, we get 1/5 cosine to the fourth power of x times sine of x plus, all right, 4 over 5 integral reduced by 2, I get cosine cubed x dx back, okay? Now I repeat the process on this. I don't know what the integral of cosine cubed is, so I'm going to kind of go off on the side and do that. So following the formula with n equals 3, 1/3 cosine to the second x sine x plus 2/3 the integral, now reduce power by 2, cosine to the first. That's something I can integrate. So let's clean this up. Sine x plus 2/3 sine x plus c. This gets subbed in for that. Don't lose sight of the 4/5 out front. So at the end of the day, our cosine to the fifth is going to be all this, 1/5 cosine to the fourth x sine x plus 4/5 this thing that we just figured out, 1/3 cosine squared x sine x plus 2/3 sine x, close that up, plus c at the end of the day. And you don't need to distribute or anything, don't need to clean that up, leave it just like it is. Okay, so the idea is to have an understanding of how to use this formula, and then ultimately not have to work too hard to get through these powers of sine and cosine. Okay, sometimes, like, you get this back, you got to repeat it and put it all together. Okay, so do your best with that. Reach out with any questions. Okay, moving on to part 2. Here we're going to focus on products of powers of sine and cosine. Okay, products, or multiplying sine and cosine together. And there's a few different cases that we're going to be looking at here. In fact, there are 4 different cases, okay? So let's take it one step at a time. Let's look at case 1. That is when the power of sine is odd and power of cosine is even. Okay, so I'm going to write it in this form. I'm going to write it as sine to the 2k plus 1 power of x. For any number k, multiply it by 2 and add 1, that's going to be an odd number. So that's just a way of representing some odd power times cosine to the nth power of x dx, where n is some even number. Okay, so basically the idea is this. Look, when I'm adding exponents, it's because I was really multiplying. Sine to the 2k plus 1 power is really sine to the 2k times sine to the first. So I'm going to do this. I'm going to make this sine to the 2k power, cosine to the nth power of x, and then that last power of sine I'm going to put off at the end here. Okay? Now, Here I have the 2k power. Well, when do we multiply powers? Really, when we have a power raised to another power. So I'm going to rewrite sine to the 2k power as sine squared x to the k power. If I had a power to a power, I'd multiply. That would be the 2k power. So I'm going to rewrite it like that. Times cosine to the nth power of x times sine of x dx. Well, now I've got the sine squared function in there. So I'm going to use a Pythagorean identity to clean that up. I'm going to make that 1 minus cosine squared x to the k power times cosine to the nth power of x times sine of x dx. And now it might not look all that great, but it actually is. Once we get to this point, we can now let u equal cosine of x, and then our du will be negative sine x dx. And so a negative du, we'll pick that up, and we'd end up with the integral of 1 minus u squared to the k power, u to the n, du, dot, dot, dot. We clean it up from there and then integrate, okay? So this is the idea when we have an odd power of sine and an even power of cosine. So let's see one in practice here. The integral of, say, sine to the 5th power of x times cosine squared x dx. Power of sine is odd. Power of cosine's even. I'm going to strip away one power of sine. So I'll have sine 4th x cos squared x. There's that other power of sine dx. This I'm going to make as sine squared to some power. Well, ultimately I want it to be the 4th power. 2 times 2 is 4, so I know that's going to be sine squared squared times cosine squared sine x dx. Now I take sine squared in the quantity, 1 minus cosine squared x, quantity squared, cosine squared sine x dx. Now we let u equal cosine x. Negative du will be sine x dx here to pick that up. All right, and so anywhere I have a cosine, I replace it with u. So we now have 1 minus u squared squared. Here's another u squared, and then sine x dx, negative du. And now we have an integral in terms of u. I got to FOIL this out first. I can now distribute the u squared through. Now I can integrate with respect to u, the negative of 1/3 u cubed minus 2/5 u to the 5th plus 1/7 u to the 7th plus c. And now at the end of the day, subbing back in for u, which was cosine x, we get negative quantity. 1/3 cosine cubed x minus 2/5 cosine to the 5th x plus 1/7 cosine to the 7th x plus c at the end of the day. All right. So, some technical stuff here by parts. It also includes u substitution. Okay. Case 2 of this is like case 1, but in reverse. Let's say power of cosine is odd, power of sine is even, like case 1 in reverse. So let's just do an example here. So we have the integral of, say, cosine to the 7th power of x, sine to the 4th x dx here, okay? So cosine has the odd power, so this is where we're going to break one cosine off. So I'll have cosine to the 6th, sine to the 4th, and then my extra cosine over here. And then for this, I'm going to make that cosine squared to an appropriate power. In this case, it would be cubed. Power to a power we multiply. 2 times 3 is 6. Now I'm going to take the cosine squared, rewrite it using its Pythagorean identity in terms of sine. And now I can do u substitution, letting u be the sine function. Du is positive cos x dx, so we're good there. So there's my u's, and we're going to get integral 1 minus u squared, quantity cubed. Here we have u to the 4th, here we have du. So same idea. Here I got to, take a moment to cube this out. And in doing so, that becomes 1 minus 3u squared plus 3u to the 4th minus u to the 6th times the u to the 4th on the outside. Distribute your u to the 4th through. And now we're good to go here. So what are we looking at? 1/5 u to the 5th minus 3/7 u to the 7th. 3/9 u to the 9th, 1/11 u to the 11th plus c, and u was the sine function. So end of the day, 1/5 sine to the 5th power of x minus 3/7 sine to the 7th power. I'll simplify 1/3 sine to the 9th minus 1/11 sine to the 11th. And there is your end result for that integral. Okay. Case 3. Is when both sine and cosine have odd powers. And in this case, the technique works either way. And what I mean is by isolating, one of the trig functions squared so as to use your Pythagorean identity. All right, so let's take a look at, suppose we have sine cubed x cosine to the 5th x dx, okay? They both have odd powers, so we can choose which one to break down. I'll go with cosine, okay? So watch, I'm gonna do this. I'm gonna go cosine to the 4th, break off a cosine, and now I'm gonna get that as cosine squared, and now I'm gonna change that to 1 minus sine squared. U will be sine du cos x dx. So this becomes u cubed 1 minus u squared du. Following suit, 1 minus 2u squared plus u to the 4th. Distribute u cubed minus 2u to the 5th plus u to the 7th. And now 1/4 u to the 4th minus 2/6 u to the 6th plus 1/8 u to the 8th plus c. 1/4, what do we use for u? Sine to the 4th minus 1/3 sine to the 6th plus 1/8 sine to the 8th plus c, and we're done. That's if we broke down the cosine. I told you it works either way. Let's do it again. Sine cubed times cosine 5th. This time, let's break this one down a little bit. Sine squared, cos 5th, and the extra sign there. I'm going to replace that with 1 minus cosine squared now. And we just get this. Whoops. Can't forget my sine function. Now I'll let u equal cos. Du will be negative sine x dx. So negative du. Negative 1 minus u squared, u to the 5th du. And here we just have to distribute, so u5 minus u7, and now negative 1/6 u to the 6 minus 1/8 u to the 8th. And replacing, we get negative 1/6 cosine to the 6th x minus 1/8 cosine to the 8th x plus c. Okay, both of these are correct answers. It was actually a little bit easier to break down the one with the smaller power. Notice it was a little less work, okay? So that's, but it'll work either way, this technique, if both powers are odd. And now the only case we haven't seen is if both powers are even. And in this case, the idea is get in terms of the same trig function and use the reduction formula. Okay, so let's take a look here. If we have something like integral of sine to the 4th cosine squared, here they both have even powers here, okay? So I'm going to break the cosine squared down into the Pythagorean identity. And now what I'm going to do is distribute the sine to the fourth. So I'm going to have sine to the fourth minus sine to the sixth. And basically what I'm going to do is I'm going to break this now into two integrals. And I could use my reduction formula to get through these. Okay? And I'll leave that for you folks to practice. Okay? You can just bring this formula up from here, do sine to the fourth, do sine to the sixth, put the two together, and subtract them. Okay? And so you can give that a try and reach out if you have any more questions. Okay? All right. So that was part 2. Moving into the final part, part 3, deals with now powers of secant and tangent. Now remember, the derivative of tangent is secant squared. And the derivative of the secant function is secant x tan x. Okay, so you want to know those derivatives. Okay, and again, there's going to be a couple of cases as far as this stuff goes. We're going to look at 3 cases of this stuff. So case 1, power of secant is even. Okay, and basically the way I say it is this. We're going to end up stripping out a secant squared x dx, and that will be reserved for du, which means u would have been the tangent function. Okay, so here's kind of the general idea. Secant to an even power, I'm going to write that as the 2k power. So for any number k, 2k is even, times tangent to whatever power n. I'm going to break off a secant squared, so I have to subtract 2 powers. Secant 2k minus 2x, tan to the nx, then times the secant squared x dx I just broke off, okay? Now what I'm going to do is I'm going to work on cleaning this up to get it in terms of tangent, because that's ultimately going to be our u, okay? So I'm going to get a secant squared out of this thing. And you got to think about it a little bit, but that ends up being the k minus 1 power. If I distribute that back, there's my 2k minus 2 power again, okay? Tangent to the nth of x, secant squared x dx, okay? Now, using the Pythagorean identity for secant squared, that ends up being 1 plus tangent squared. All right, so we have 1 plus tan squared. Quantity to the k minus 1, tangent to the nth, secant squared x dx. Now we use u sub. U is the tan function. Du picks up the secant squared x dx. That's the idea here. Okay, so let's see one in practice. Suppose we have the integral now of secant to the 6th power of x tan cubed x dx. Okay, so I'm going to break this down by 2 powers. That's going to leave me with secant to the 4th, tan cubed, secant squared x dx. I'm going to write secant to the 4th as a power of secant squared. In this case, it would be secant squared squared. Now I'm going to replace secant squared with its Pythagorean identity, 1 plus tangent squared x. Now I'm going to let tan be u, and du picks up that secant squared x dx at the end there, okay? So this is just going to become 1 plus u squared, u cubed, du. Okay, following like what we did before, we got to clean this up a little bit before we can integrate. Distribute. We're good to go. 1/4, and look, at this point I'm going to sub my u back in as I go. U was tan, so 1/4, tan to the 4th x plus 2/6, tangent to the 6th x plus 1/8, tangent to the 8th x plus c. And now we're done. All right. Case 2 out of 3. Case 2 out of 3. powers of secant and tangent are both odd. Okay, this time what we're going to do is we're going to strip out a secant x tan x dx, and that's going to be our du. So what does that mean? U is going to end up being secant x this time. Okay, so again, here's kind of in general, we have like secant to the mth power of x, where m is some odd number, and then for tangent, I'm going to write that as the 2k plus 1 to represent the odd number there. Okay, I'm going to break out a power of each. So this becomes secant to the m minus 1 power of x, tangent to the 2k power of x, times the extra secant x tan x dx. Okay, I took away 1 power from each of the previous. Okay, now it's the tan one that I want to get in terms of secant here. So this becomes secant m minus 1 times tangent squared to the k times secant x tan x dx, and now I can use my Pythagorean identity and get integral secant to the m minus 1 power of x. Okay, tan squared becomes secant squared x minus 1. And now we let u equal secant x. Our du picks up that secant x tan x dx at the end of this thing. Okay, so these are u's. There's my du. We get u to the m minus 1 power. U squared minus 1 to the k du. And then again, we clean it up and we go from there. Okay, so let's see one in practice. And again, it's going to just take some time doing these to really get them down. Fortunately, you don't have to really memorize these. You can have these formulas handy and these notes handy when you're doing these problems, okay? You don't really have to memorize these techniques. You just got to be able to identify, given an integral, which one of these am I using, okay? So here, let's take a look at, say, secant cubed x, tangent cubed x. They both have odd powers, okay? So since they're both odd, I'm going to break them off 1 each. That'll bring both of these down to the second power. There's my secant x tan x dx that's going to stay on reserve for du. All right, it's the tan function I want to rewrite in terms of secant here. Well, that is tan squared, so I don't have to worry about another power here. That by itself is just going to become secant squared x minus 1. Okay, and now I'm going to let u be secant x du secant x tan x dx. So that's a u, there's my du. So this becomes u squared, quantity, u squared minus 1, du. All we got to do here is distribute. And now we can integrate 1/5. What was u here? U was secant, so 1/5. Secant to the 5th power of x minus 1/3 secant to the 3rd power of x plus c. And hopefully you've stayed in it this long because we've made it to the final case of these things. And this is just powers of tangent. Okay, no secant whatsoever, just the power of tangent. Okay, and so let's suppose we have tangent to the nth power of x dx. Okay, what we're going to do is break off a tangent squared. So I'm going to take off 2 powers of this. All right. And I'm going to replace tan with secant squared x minus 1. Okay. Now what I'm going to do is I'm going to distribute this. So we're going to have integral tan to the n minus 2 power of x secant squared x minus tan to the n minus 2 power of x. I'm going to break this into 2 separate integrals now. We have the integral of tan to the n minus 2 power of x secant squared x dx minus the integral of tan to the n minus 2 power of x dx. For this, we use u substitution. U is tan, du will pick up the secant squared x. On this, we repeat the process if need be. All right, meaning we got now another even power, or another power tan. We're going to break that down and see what happens, okay? So again, let's take a look at an example. Let's do the integral of tangent to the 4th power of x. Okay, we want to break that into tangent something times tangent squared. So in this case, this is just going to be tan squared x times tan squared x dx. Okay? Now we're going to take the second tan squared and we'll replace it with secant squared x minus 1. I'm going to distribute. And now I'm going to break into two separate integrals. This is going to become the integral of tan squared x secant squared x dx minus the integral of tan squared x dx. This I can use u sub on. So that becomes u squared du. Okay. Minus, now I have this tan squared one, so I'm going to kind of repeat the process. Well, notice it's just tan squared. So since I have that, I'm going to replace that with secant squared x minus 1. That is something we can integrate. Secant squared x by itself just goes back to tangent. Negative 1 by itself goes back to negative x when we integrate. So we're good to go here. Look, we're going to get 1/3 u cubed minus the integral of secant squared is just tan x. The integral of negative 1 is negative x. Careful with your parenthesis there. Plus c. At the end of the day, I'll write this as 1/3 tan cubed x minus tan x plus c. And there you have it, folks. So a whole lot of fancy trig integrals, lots of powers, special cases, special techniques based on what the case is, okay? So take some time to go through these. Send me your homework, and let me know if you have any questions. All right, folks? Have a good one.